Thanks, everyone. My name's Kevin, representing Brookhaven National Laboratory for an abridged site report with a focus on Condor. This talk was co-authored by Tom and Chris. We're going to give a general site overview. We're going to talk about the recent expansion of our computing fabric, the Condor Upgrade, and some improvements and redesign of some custom monitoring. So let's dive in. The Scientific Data and Computing Center is at Brookhaven National Laboratory. It's an outgrowth of the relativistic heavy ion collider through the mid to late 1990s. So quick history lesson, where originally the RIC computing facility we developed and grew to support Atlas, became the RIC Atlas computing facility. And we've recent years been attracting more stakeholders and expanding our services, and we've rebranded as the Scientific Data and Computing Center. So we are the tier 0 for our home collider, the RIC. We're a US tier 1. We support the National Synchrotron Light Source 2 at BNL and the Bell 2 experiment for KK in Japan. We're providing computing and storage for ProtoDune, Dune, along with FNAU, and serving data to all Dune OSG sites. We're also providing computing resources for various smaller R&D experiments in nuclear physics and high energy physics. We're serving more than 2,000 users over 20 projects. We're developing and providing admin collaborative tools such as Imbinio, Jupyter, BNL Box, Discourse, Git, Mattermost, etc. SPhoenix is our latest experiment for evolution of the RIC, Phoenix++, I guess. And BNL was recently selected as the site for the upcoming major new facility, the Electron Ion Collider, EIC ERIC, in partnership with JLab. So a little bit overview of high throughput computing at SDCC. We're providing our users with over 1,700 HTC nodes. We have approximately 121,000 logical cores. It's all managed by HTCondor. So echoing Fermi, thank you very much to enable this. All nodes have been running Scientific Linux 7. And we're in preparations, everyone's well aware of the up in the air with the Linux. We're in preparations for an OS upgrade to most likely Alma Linux 9, keeping an eye on CERN and Fermi. And our upgrade from 9 to 10 is almost finished, in progress. The Atlas pool is about 500 HTC nodes with 35,000 logical cores. And we have shared pool with about 1,200 HTC nodes and 86,000 logical cores. The Atlas Tier 1 worker nodes were upgraded to Condor 10, and a large portion of this pool is the new Supermicro, what I touched on, our new expansion of our computing fabric. So this just hit the floor. So on that point, the computing expansion for 23 was historic. It was our largest computing expansion to date. We purchased 648 Supermicro, 1 new nodes for Atlas and the RIC experiments, with about 62,000 logical cores just on the floor. It's housed in 20 racks. The system specs are given. We will be receiving some Supermicro ARM for eval. We have 2 systems on order that are the topic of Tom's technical talk yesterday. If you didn't catch it, you can check out the presentation materials, please. So these are going to be Ampere Ultra. And yeah, the nodes are, again, SL7 with Condor 10. So the important point here is all of the new expansion, we just went right to Condor 10. And moving forward, we, at this time, rolled out the Condor Upgrade for the rest of the components. So the tricky issue here is we have various experiments with different production schedules and not really much in the way of downtime. So we tried to do this in a way that was painless for us and the end users and as transparent as possible. So to minimize downtime, we upgrade the systems in batches, several racks at a time. Chris and Tom developed a simple but elegant approach where the nodes drain out, and with some automation, do the upgrade, and within about 2 days' time, the majority of the nodes are back in the pool, and to a max where all of them within about 4 days. So we targeted to do this in stages where we prioritized the execution hosts. Once all the workers were upgraded, then we moved on to the CEs and the interactive submit nodes, and then finally at the last stage, the collector negotiators. So we tested in preparation, did a lot of testing about cross-version compatibility before we proceeded in production. You can kind of see on the matrix, each row is a stage of the testing the interoperability. So we started with keeping the collector negotiator and the SCED on 9, along with the CEs, and moving the execute nodes to 10, or to a mix of 9 and 10. And we sort of progressed from right to left in each row, where here we have the SCED and CEs at 10. Eventually we have the interactive submit also at 10, and we kind of finish up with everything at 10. So here's our status today. The Atlas Tier 1 workers are done. The new computing expansion is up to 10. And we've tested the next gen CE. In progress are the Atlas CEs and the shared pool execution hosts. And remaining to do when we get back in town, we'll finish up again with the shared pool CEs, all collector negotiators, and all interactive submit. All right, and then so for the next stage of the talk, we'll talk a little bit about monitoring. So we still use a lot of traditional Nagios, Grafana, Ganglia, but we'll talk a bit now about Elasticsearch. And so I'd like to start with the diagram here. So some of you may already be familiar, some of you may have no idea about this, but you just at a high level, you have sort of a data source up top. And then at this level, there's sort of an ELK cluster. We have 4 servers, and the components are Elasticsearch, Logstash, and Kibana. And so Logstash is really the magic here. There are 3 components to the Logstash: an input, which is a data source, and then there's a filter layer, and then finally an output. And so we output the Logstash to these instances of Elasticsearch, and then there's a Kibana front end. So we inherited a similar application. The earlier work served us well, and eventually it was time for a hardware refresh on the ELK components. And at that time, we reevaluated and redesigned the architecture of this monitoring tool. So previously, the FileBeat service was running on all of our execution hosts. And I showed you a moment ago with the intro how large is the size of our Linux farm. So we redesigned this, so it's an order of magnitude more to have, say 2,000 plus hosts all shipping out their shadow log. So instead, we kind of redesigned this. Now we have about 100 hosts that are shipping their FileBeat services running there and shipping out their SCED log instead. All right. So the input source is the log file, the SCED log. The output is sent to the Elasticsearch service. And now we can run this on one instance of Logstash. We no longer need multiple instances of Logstash, or previously we had this Lumberjack plugin, which would allow a multi-Logstash. It kind of simplifies and cleans the architecture a bit. So 2 components are Grok and Aggregate. These are both Logstash filter plugins. Grok, I just love that word and the naming of things. I don't know how many science fiction readers are in here who remember Robert A. Heinlein, Stranger in Strangeland, I believe it was. But Grok is great for unstructured data source. So for example, you can imagine the SCED log is really just every row of the SCED log has a different structure, right? So it's an unordered or unstructured data source. But there are elements or rows of data that are of interest. So for example, everyone has commonality or common denominator. They all start with a timestamp. They all have next job ID. And then the message that follows has various properties or various structures. So we can define a Grok pattern, which is somewhat like a regex, and that can capture or grab or tag or index the components that we're looking for. So there's a little bit of a illustration of the Grok debugger, which is in the dev tools section. So you can see as a sample data, this is just a row of the sched log. And then as the Grok pattern, this is sort of like grabbing the date, grabbing the job ID. There's some static text that follows, started, shadow for job, right? We're not really grabbing any of that, but we're kind of parsing it. And then you can see like we're able to grab the job ID, the email address, the IP, et cetera. And you kind of see below how it looks here. The other Logstash filter plugin that we used was the Aggregate. So the idea behind this is that we want a key on the job ID, and every message in the log file with that job ID has part of what we're looking for. So thank you, 5 minutes. So yeah, so we're kind of like, we're building a map the first time we see the job ID, and that's created and stored in memory here. And then as the job ID, as messages come in with that job ID, and we're grokking pieces of them, we're kind of like aggregating them all together. And then finally, you can see at the end, we set the event fields from the map and delete the map. And this allows a nice front end in the Kibana. We don't kind of give you a quick workflow. You come into the Kibana and you select the fields you're looking for. So these are typically the ones we look for: job ID, agent host name might be the source, or the CE, for example, or the interactive submit host name. The user who ran this job, the execution host that it's running on, and then of course we're looking for the shadow exit codes. And this is a powerful tool that allows us to assign different operators to the selected fields. So for example, in this demonstration, I'm looking for, in the past 1 year, all instances where the shadow exit code exists. You can see there's about 231 million records of completed job this past year. This is very useful for example, if we come in one morning and there unexpectedly is a subset of the farm that's crashed overnight, we want to sort of investigate and see, is this, maybe it was a user, maybe, I don't know, maybe we try to understand, get some, I know yesterday in the bracket, it was a little bit more popular choice for the error propagation, but for admins of a large cluster, this observability is very powerful. So yeah, just kind of wrapping up in summary, the SDCC provides batch computing capacity of over 120,000 cores to 2,000 users in more than 20 projects. And we've been leveraging the power of HTCondor for 2 decades. Again, thank you. Our upgrade to 10 is in progress in a rolling manner to minimize downtime and be transparent to the end users. And it's already completed on all Atlas Tier 1. And we've made some improvements and implemented some custom elk monitoring of Condor jobs. We spoke briefly with Miron and Jason. I'd love to speak with you more, Todd, or I think James. I don't think we've met yet, but if you're using the Condor ad stash or doing any other sort of clever Elasticsearch or any other novel monitoring, please don't be shy. We'd love to speak with you, answer questions, and kind of see what you're doing too. So I'd like to just save a moment for questions and comments. Thank you all for attending. Special thanks to Chris and Tom.